In this video, we will learn how to find the derivative of composite functions using the chain rule and the general power rule, which is just a specific case of the chain rule. We'll also be simplifying derivatives using algebra, and we will also apply the chain rule to differentiate trig functions that are also compositions. So we begin with this table here, and what the table does is it shows functions that we already know how to differentiate without the chain rule. Notice that none of these functions here are composite functions. And so what do I mean by that? Well, composite functions are functions within functions. So if we look at the functions on the right side of the table, we can see the difference. For example, on the left side, we simply have cosine x, where the inside of cosine is just x. On the other side, its counterpart, we have cosine 3x, where the inside of the function is now not just x, it is 3x. That is a composite function. So we can see those similarities throughout these examples. So now let's look at the chain rule and how the chain rule tells us to take the derivative of a composite function. So this notation here means that the function g has been plugged into the function f. And the chain rule says to take that derivative, you have to differentiate between the smaller function that's on the inside and the larger function that's on the outside. And I use those words very loosely and informally, as in the sense that the smaller function is the one going inside of the bigger function. So what it tells us to do is to take the derivative of the large function, plug in the small function, and then multiply by the derivative of the small function. The general power rule says the exact same thing as the chain rule. It just simply applies when the larger function is a power function, just like it is in example 1. So in example 1, we can see that we have this smaller function of 5x minus 2 being plugged into this x to the 3/4. So how do we take the derivative of this? The chain rule tells us start taking the derivative of the larger function, of the power function. So we're going to begin with the power rule and bring this exponent of 3/4 down in front. We're bringing it down in front of the 5x minus 2. And the new exponent needs to decrease by 1. So we have a new exponent of 3/4 minus 1. So far this feels very familiar to the power rule. Only difference we saw here is that what's on the inside was not just x. Now what the chain rule comes in and tells us to do is that we also need to multiply by the derivative of that inside part. So I also need to come out here and multiply by the derivative of that 5x minus 2. So now let's come in and simplify this. We have that y prime is equal to 3/4 5x minus 2 raised to the negative 1/4 power, all multiplied by 5, because the derivative of 5x minus 2 is in fact 5. I'll simplify this a little bit more by multiplying the 5 with the 3/4 in front, leaving us with 15 over 4. And then to deal with the 5x minus 2 to the negative 1/4 power, we will write that as the 4th root of 5x minus 2 in the denominator. And I put it in the denominator because the exponent was negative. Example 2, we want to find the derivative using the general power rule. I'm first going to rewrite this function so that it looks like something we would approach with the negative power rule. And I'm going to do that by just eliminating the fraction form of it and bringing up the factor in the denominator and changing the exponent to negative. So now to find y prime, we are taking the derivative of this power function. Now the general power rule here, we have something very similar to this, of u to the n, right? So notice I'm disregarding this negative 5 because the constant multiple rule says it will just come out and be multiplied by whatever we get. General power rule says we need to bring our exponent of n down So I'm going to bring the exponent of negative 3 down. What's on the inside of the parentheses, the 5 minus 4t stays the same. U stays the same, but the exponent of u decreases by 1. So our new exponent is now negative 4. And then on the outside, we have to multiply by the derivative of u, just like we did here. We now have to multiply by the derivative of 5 minus 4t. I'm going to go ahead and multiply this negative 5 and this negative 3 to give me a positive 15 in front. And I'm also going to go ahead and rewrite this 5 minus 4t to the negative 4. And I'm going to rewrite it by putting it in the denominator with an exponent of positive 4. As for this derivative that we picked up from the chain rule, the derivative of 5 minus 4t is negative 4. The last thing I will do is multiply the 15 and the negative 4 to give us our final answer for y prime. In example 3, we are going to begin by finding the derivative, and then we are going to simplify that derivative completely. We have our function f of x, and this function is a product. We have two factors that are being multiplied together. And so we are going to begin with the product rule. So we need to identify f, and we need to identify g. We'll find f prime, and we'll find g prime, because the product rule tells us that our derivative, f prime of x, is going to be f prime g plus g prime f. And please do not confuse this f, which is the original function, with this f, which is going to be the first factor from our product of x squared. And then our g will be the second factor of 1 minus x squared. I'm going to rewrite that as 1 minus x squared to the 1/2 power, because it'll be easier for us to see how the general power rule or the chain rule is applied right there. To take f prime right here, this is just a basic power rule. I'll just bring the exponent of 2 down and decrease the exponent on x to 1, so we don't see it anymore. But to take g prime here, what we have on the inside of the parentheses is not just x, and so we're going to need to use the general power rule or the chain rule. So this exponent of 1/2 still does come down in front, and we keep everything that we had on the inside the same. The new exponent decreases by 1, and the chain rule tells us that whatever was on the inside of the parentheses that was not just x, you need to multiply by the derivative of that. So we have the derivative of 1 minus x squared hanging on the outside there. Let's go ahead and simplify this. This new exponent on this 1 minus x squared is going to be a negative 1/2, and the derivative of 1 minus x squared is negative 2x. These 2's can cancel. It leaves us with negative x. This 1 isn't going to change anything. And all of this here has a negative exponent, so I'm going to put it in the denominator. And the exponent is a 1/2, and so I'm going to put it under the square root. So now we have all 4 of the pieces that we need in order to fill out what f prime of x is, this f prime g plus g prime f. So we have f prime multiplied with g, so that's f prime times g. So that's 2x times the square root of 1 minus x squared. And then to that, we are going to add g prime f. Here's g prime. Multiplying that by f is going to give us a negative x cubed in that numerator. So I'm going to erase this plus sign and put a minus x cubed in the numerator. The denominator will still be the square root of 1 minus x squared coming from there. So we have our derivative. Now I'm going to work on simplifying it completely. We have 2 separate terms. I want to combine them into one fraction, and so I'm going to need a common denominator. Down here, this denominator is only a 1, and so in order to make a common denominator, I'm going to be multiplying the denominator and the numerator here by 1 minus x squared. And I do that because this already has a denominator of 1 minus x squared. So now they have the same denominator, oh, not 1 minus x squared, but the square root of 1 minus x squared. Excuse me. So now they have the same denominator. This fraction has this numerator. So there's the 2x, and then there's the 2 square roots of 1 minus x squared that we multiplied together. So the square root will cancel and just leave us with 1 minus x squared. And then we have a minus x cubed. I'm going to go ahead and distribute that 2x. And now I'm going to combine my like terms in the numerator. And now to finally finish my simplifying this, I do have a GCF in the numerator that we can factor out, least common factor of x, which leaves us with this final simplified answer. In example 4, we have a function that is a quotient, and so we are going to use the quotient rule, and then we are going to simplify the derivative. So to begin with the quotient rule, I am going to identify what my f and my g are, which are the numerator and the denominator of the function. G is a power function, but it doesn't look like it with that radical, and so I'm going to rewrite the denominator of G as x squared plus 4 all to the 1/3 power, because the cube root is the same thing as an exponent of 1/3. So being that we are going to be using the quotient rule here, we are going to need to calculate f prime, and we're also going to need g prime, because the quotient rule tells us that our overall derivative for our function, f of x, remember this f prime has nothing to do with that f prime, is going to be f prime g minus g prime f, all divided by g squared. So taking f prime and g prime, the derivative of x is equal to 1. And for g prime, we're going to need to use the generalized power rule, bring our exponent of 1/3 down, keep the inside of the parentheses x squared plus 4 the same. The new exponent needs to decrease by 1. 1/3 minus 1 is -2/3. And chain rule says that we multiply by the derivative of whatever was on the inside. And the derivative of x squared plus 4 is 2x. So now I'm going to simplify this g prime. Okay, and I know that this still has the negative exponent in there. We could fix that now or later. I'm going to choose to fix it later and go ahead and plug it in to the quotient rule here. So we have f prime g, which will be 1 multiplied by this cube root, so that's not going to change anything. And I am going to write it with the 1/3 power because it will help us when it comes to simplifying. From that, we are going to subtract g prime f. So this is going to be multiplied by f. So I'm going to end up with a 2x squared here when I multiply those x's there. Denominator, we have g squared. So we're taking this and squaring it, which means we're going to multiply the exponent of 1/3 by 2, and it will become 2/3. So now I'm going to start to simplify this expression. There's a few things I want to do to simplify it. One, I want to get rid of this fraction within the fraction, and so I'm going to come in and multiply every term in the fraction by 3. So I'm definitely getting rid of that. I will end up with a 3 in front of that first term, and I will also end up with a 3 in the denominator. So one, I hope everyone realizes there are 3 terms here in this fraction, 1, 2, 3, and I could come in and do the 3s if I do them to every single term that's in the fraction. Okay, so the next thing I'm also going to do in the numerator, I'm going to factor out the GCF. Both the numerator have this x squared plus 4. In the first term, it shows up with an exponent of 1/3, and in the second term, it shows up with an exponent of -2/3. We have to factor out the smaller, and so I'm going to be factoring out the x squared plus 4 raised to the -2/3. We'll see what that leaves us with in the numerator, and in the denominator, we know we have this 3 times x squared plus 4 to the 2/3. So now to figure out what's left on the inside of the parentheses, well, from the first term, we had a 3. And we had an x squared plus 4 to the 1/3, and we took away negative 2/3 of them. So 1 minus negative 2/3 is a positive 1, because that's 1 plus 2/3. And so here we have x squared plus 4 just to the positive 1. And then in the second term, we had this negative 2x squared. We still have that. And the exponent on this x squared plus 4 was negative 2/3, and that's exactly what we factored out. So we're simply left with only the negative 2x squared. So now we can simplify this a little bit further. Here we have this x squared plus 4 to the negative 2/3. I'm going to send that entire factor to the denominator so that this 2/3 will become positive 2/3. It will then combine with the x squared plus 4 to the 2/3 that's already down there to give us x squared plus 4 to the 4/3. So we've dealt with this in the numerator. We still have that 3 there. As for what we have here, distributing the 3 would give us 3x squared plus 12. And then I'll combine like terms with that minus 2, leaving me with x squared plus 12 in the numerator. In example 5, we are going to be taking the derivative of a power and simplifying it. So I can notice that I have this quotient on the inside here, yes, but this quotient all has an exponent on it. So in order to start taking this derivative, we are going to begin with the power rule. So the power rule tells us that we pull this exponent of 2 down in front. The new exponent on everything that we have decreases by 1, so it's now 1. We don't typically write that. But everything that was on the inside of this power was not just x. And because it was not just x, we then have to apply the chain rule. That tells us to multiply by the derivative of whatever it was that was on the inside. Now, what it is that was on the inside is a quotient. So in order to take this derivative, we are going to need to use the quotient rule, where we identify f as the numerator and g as the denominator. We can use basic derivative rules to take f prime and g prime. Then I'm going to come down here and fill out what the quotient rule tells us the derivative is. The quotient rule tells us the derivative of a quotient is f prime g minus g prime f all over g squared. So we are going to calculate this derivative by filling out f prime g minus g prime f all over g squared. So f prime multiplied by g. From that, we will subtract g prime multiplied by f. And in the denominator, we will have g squared. And now it's a matter of us simplifying. I'm going to begin by distributing this 2. And then in the second fraction, we will distribute this 3. And we will distribute this negative 2x. Our denominator stays the same. I'll go ahead and combine like terms in this fraction here and multiply straight across the top and straight across the bottom. So we have the 6x minus 2 from the numerator of the first fraction. When I combine like terms in the numerator of the second fraction, I'll combine this 3x squared with that negative 6x squared to give me a negative 3x squared. And then we'll have our plus 2x and our plus 9. In the denominator, we will multiply this x squared plus 3 with this x squared plus 3 squared to give us x squared plus 3 cubed. And there is our simplified derivative. Finally, we have an extension of our rules for differentiating trigonometric functions that now applies to composed trig functions. So what that means is we have seen all of these rules before, but when we saw them before, they only had an x on the inside. They didn't have a u on the inside. They just had an x. and they didn't have this u prime, because if this is just x, then u prime would just be 1. So this is extending to now using functions where u is a function of x. So it's not just x on the inside, it might be 2x. So for example, in 6a, if it's a 2x on the inside of a sine function, you still take the derivative the same way you take the derivative of sine, and you get cosine 2x. So it should still be a 2x on the inside of that cosine. But the difference is the chain rule tells you to come on the outside and to multiply by whatever the derivative of that inside was. So we would come on the outside and multiply by the derivative of 2x. Well, the derivative of 2x is 2. And I'll just stick that 2 in the front of this cosine 2x. In example 6b, it's not just x on the inside of this cosine, it's an x minus 1. But it is cosine, so we still take the derivative the same way we take the derivative of cosine. So we have a negative sign that we get for the derivative of cosine. We get a negative sign. The inside should stay the same, so we still have x minus 1 on the inside. Chain rule tells us we need to multiply by the derivative of that x minus 1. Well, the derivative of x minus 1 is just 1, and so that won't change anything. This will just be negative sign of x minus 1. Finally, we have tangent of 3x. The derivative of tangent is secant squared, so y prime will be secant squared of 3x. But this is not just x on the inside, and the chain rule tells us that we need to multiply by the derivative of that 3x. And the derivative of 3x is 3, and so we are left with 3 secant squared 3x. At the bottom of this page, we have a summary of the derivative rules that we have learned so far.